The subject of my presentation is actually describe the principle behind the device, the platform which I've developed, as well as description of the setup which illustrate how the platform works. The platform in question is what we call an InfraRed scene projector. This is the device which provides dynamic infrared scenes. To start with, I will describe the basic elements of our setup. Element number one is a visible projector. Actually, the starting point is feeding the visible image into this projector, the dynamic scene. The second element is a chip, which we call the converter chip. And finally, the third element is the device under test, which in this particular case is an infrared camera operating at 10 micron wavelength. The concept is the following, or the function is the following. The sequence of video is being fed into the projector, like in a home theater. The projector projects the visible image onto the chip, and the chip literally works as a converter from visible light to the infrared light. So the light, the image projected, or the video sequence projected on the chip is then re-emitted by the chip at a different wavelengths corresponding to the infrared, either in mid-infrared or long infrared. And the camera used in the setup is actually used here to record the infrared image generated by the chip. So again, the chip is totally passive. All what the chip does is essentially it converts the visible video sequence into the infrared video sequence. Now, in few words, I would like to describe the chip by itself. In this particular case, we have a chip consisting of 288 by 384 pixels, 35 micron pitch. Actually, if you would have a microscope, or even better, the scanning electron microscope, you could see individual pixels. And actually, these two photos here on the screen represent the pixels. On the first photo, you see a multitude of pixels. On the other photo, you see actually a single pixel. Again, each of these pixels resemble like a micro platform, or in other words, like a small table. It is supported by two legs over the substrate, which in this particular case is a wafer of silicon. Actually, this is represented by the drawing called here figure number 2. Okay, so you have this micro platform which has this tiny shape, tiny size of 35 micron by 35 micron, which has a thickness of a fraction of a micron, and which is supported by two legs, which have a diameter in the range of few microns. What is happening here? When the projector projects the visible image onto the array of these micro platforms, each of these micro platforms receive the visible signal. The visible light is being absorbed by each individual pixel according to what is sent by the visible projector. Now, in each of the pixels, the absorption of the visible radiation causes an increase in temperature. So basically, the temperature of each pixel increases, and the pixel starts to radiate the infrared radiation. Each of individual pixels works like a black body with a Lambertian distribution of radiation. So generally, when the temperature of each pixel increases, its emission curve basically is exactly the same as a black body, which means it's basically a Planck curve. And you see that the peak of emission changes depending on its temperature, exactly like the black body would behave. Now you have a combination of all these pixels, and at the end, the whole complete image, the whole frame of the visible image is converted into an infrared image recorded by the camera. Actually, the recorded sequence of video will show both the video image as well as the infrared image. Please notice that the chip is actually packaged in a small, I would say, enclosure, which you see over there. The enclosure is vacuum tight, and as you can notice, there is a small tube protruding from it, which is connected with the tube to a small pumping system. Actually, in this particular case, there is a small vacuum pumping setup, and we are pumping air from inside the enclosure. This is a very important aspect of that. Actually, the chip can only operate basically at reduced pressure, ideally in vacuum. It is quite understandable because the principle of conversion from the visible to the infrared is based on the absorption of radiation, increase of temperature, and then emission of radiation. Obviously, thermal isolation of each individual pixels, which will be heating with the visible radiation, is of great importance. And actually, for this purpose, the chip has to be operated in vacuum, which provides ideal conditions of isolation. Thus, the operation of the chip actually depends uniquely on its architecture, and in particular, for each individual pixel, it depends on the support of each of the micro platforms. So again, there is no electronics underneath each pixels. The chip is completely passive and really works like a converter. It converts visible image to the infrared image in both wavelength bands. It can be made wideband, in a sense, emit radiation both in the mid-infrared as well as the long infrared, but it could be also narrowband. It could be tuned to one of these two bands, and everything depends on its architecture and generally the design. Now, it is also possible that the input image actually also represents the infrared imagery. So we see that practically the chip reproduced whatever type of video signal which is being projected on it. I mentioned here that in this demonstration setup, the visible light and the imagery, the dynamic scenes, are projected by the visible projector. This is typical off-the-shelf projector. It is also possible to use other light sources. You can imagine using a laser which would shine on the chip, again, on the same principle, would hit individual pixels. The pixels would start to radiate infrared radiation, and device under test, camera could actually capture this radiation. We can also imagine that we would use multiple sources, such as visible projector, combined with a laser, or combined with multiple lasers. I have to say that there is a lot of flexibility in terms of design of the chip. Depending on the application, we can control the following parameters. We can control the number of the pixels, we can control the pitch, and in terms of the numbers, we can even think about 4K type of resolution. In terms of the size of individual pixels, we can vary them typically between 17 micron by 17 micron up to about 35 micron by 35 micron. Now, in this particular setup, we are not controlling the temperature of the chip. There are no provisions for this control. However, we can install the thermoelectric cooler or any other type of device at the back of the chip, and at this time we can not only project the infrared image, but we can provide a background which is at much lower temperature, even temperature below 0 centigrade. The frame rate of the whole setup depends on two factors: on the speed of the chip and the speed of the projector. Actually, in our design, the chip is always faster than the projector being used. So actually, we can think about the operation approaching 600 hertz and maybe even more. This goes back to the response time of the chip. We can produce the chips with the response time down to about 2 milliseconds or even below a millisecond. The very important parameter of the chip is what is called an apparent temperature. This is a temperature of a black body which would emit exactly the same type of radiation. Our testing showed that the chip which we can produce can achieve the apparent temperatures in the excess of 700 Kelvin, actually approaching 800 Kelvin, both in the mid-infrared and the far infrared. We expect that with the optimization of the chip design, we'll be able to reach 1000 Kelvin as apparent temperature in both bands. In such a way, we can achieve the operation of the complete setup, which would surpass in terms of performance everything which exists at present on the market. There are further improvements also possible, but even with this arrangement, actually we achieve the performance which can be quite suitable for multiple applications, including testing of infrared devices, infrared imagers, as well as integral part of the systems in the loop for other applications. The video frames recorded will show the quality of the image obtained. We will compare the image fed into the chip, the visible image, as well with the infrared image, both in examples of static images as well as complete video sequences. Here we show the examples of the function of our demonstration setup. Actually, what you see right now is a split screen. On the left side, you see the visible image being projected on the chip, and on the right side, you see the infrared image recorded by the camera. Actually, in this particular case, the projected image is a static 4-bar pattern, which is usually used for characterization of the infrared devices such as cameras and other type of imagers. And as you can see from both pictures, that there is a high fidelity in terms of correspondence between the image projected as well as the image generated by the conversion chip. Now we show a second example, and in this particular case we are talking really about the dynamic stent projection. Again, on the left side you see a video sequence, actually visible video sequence, and on the right side you see a reproduction of the same video sequence when they generate at the infrared wavelengths of 10 micron as recorded by the infrared camera. In this particular case, for the fans, this is Blade Runner 1 movie, very popular a few years ago. Again, you can enjoy the visible image on the left and the infrared image on the right. The second sequence show a little bit a different scenario. Actually, the image being fed into the visible projector is the image recorded in the infrared. So actually, we see a conversion of the image recorded in the infrared. Now it's being transformed into visible image. In the visible sequence, visible image is being projected on the chip, and the chip again is transforming it basically from the visible to the infrared. So in a sense, when you observe the split screen, on the red side you see the infrared image being fed into the projector, and the right side you see the infrared image generated by the converter chip.